But there's some stuff which is a little different, so hopefully that'll be interesting. That's the stuff that I'll get to at the end because I felt like I needed to connect it to adiabatic quantum optimization, as that was the title that I gave Umesh at some point. So I have a few thoughts about that at the end. What I want to start with, though, is to actually just tell you that what we heard about in the first talk this morning, or at least the final conclusion, is completely wrong. That is that exponential complexity, whatever that means, of quantum mechanics can extend to maybe not high temperature, but high energy density. Okay, I'm going to be vague about exactly what that means, but hopefully it'll be clear why I say that. In the intro part of this talk, which is going to be just sort of an intro, some perspective on what many-body localization is from a physics point of view. And then I'll tell you in the middle of the talk about a really sort of pathological model that we've been studying as a mean field sort of analytically tractable approach to understanding this phenomena of many-body localization. And then I'll make some comments about how it connects to adiabatic quantum optimization, maybe as I go along, and a couple conjectures I came up with while thinking about it this week. So this is work done, or the technical part of this is work done in collaboration with Arijit Pal at Harvard and Antonello Scardicchio, who is at ICTP currently on sabbatical on the East Coast, though. So what's the motivation? So it's actually fairly fundamental. Statistical mechanics, the whole topic, relates thermodynamics, things that you can observe in big systems, to the microscopic world. And the starting point for deriving the Gibbs distribution, the Boltzmann ensemble, is arguments about exchange, that basically systems come to equilibrium, and in order to do that, they have to be able to exchange between a system and environment all of their conserved quantities, energy, particles, things like that. Okay? So what if there is no environment, and we just have a closed quantum system? This is perhaps why my talk is different from Jens's talk, where he hit it over and over with Lindblad operators. So, well, an ergodic system, which I'll define sort of in a moment for you, is a system which behaves as its own bath. So in particular, if I imagine some big physical system which has lots of interacting degrees of freedom, then there can be some quantum spins or electrons or whatever we want to think about usually in our idealizations, but there's also some environment which is phonons in the lattice or fluctuations of other coupled degrees of freedom. And we usually treat that in sort of this Markov approximation or something analogous to it, that it's thermal. But you could also include everything, put everything into your Hamiltonian and say that, you know, the universe is quantum mechanical. Really, it's just closed system unitary dynamics. So what does it mean for this system to behave as its own heat bath? Well, the idea is that a quantum system thermalizes, or the notion of thermalization is that subsystems, finite subsystems of this larger system, will go to thermal equilibrium at long times. Okay? That's how you can define a notion of thermalization despite having unitary dynamics for a system as a whole. Okay? So let me unpack that a little bit. I'm imagining that I have some system dynamics which are unitary, and I'm only going to consider finite subsystems. I look at those finite subsystems at long times, starting with any initial conditions I want, and actually any finite subsystem I want. And thermalization would imply that the limiting behavior of that subsystem density matrix agrees with the equilibrium density matrix that I would calculate at appropriate temperature, chemical potential, et cetera, for the conserved quantities, the globally conserved quantities in the system. Okay? So, as I said, this idea of thermalization ought to be true for all finite subsystems and all initial conditions consistent with the conserved quantities. And if it is true, then that's ergodicity in the quantum setting. That's how we can justify quantum statistical mechanics, writing trace e to the minus beta h as a useful thing to do to calculate observables. So this leads to something known as the Eigenstate thermalization hypothesis, which is that for a system to equilibrate from all initial conditions, all many-body eigenstates need to agree with equilibrium on the subsystems. Okay? So here I have a closed system, Hamiltonian. That's the full Hamiltonian of the full system. I have many-body eigenstates, EI, and I again look at the reduced density matrix of a subsystem, but in this eigenstate. This is not the ground state. Actually, there are no ground states in my talk, so don't get confused. Okay? I'm always at very high energy. But in these high energy density states, high energy states, when I look at subsystems, in any many-body eigenstate, I'd expect it to look like equilibrium if this hypothesis holds. So, as the title of the slide suggests, this is a hypothesis, and it, I don't believe, has been proven in any particularly interesting models. It's sort of heuristically believed in lots of cases, and there's numerics that have investigated it in a number of settings. Yeah.
So are you talking about the unitary evolution, or?
Yep. So there's just a Hamiltonian.
So what about cyclicity? So I understand that there is long time and very long time. So does it? So eventually it should return to where it started. No?
So technically, I want to think about a very big system, and let me. So the many-body level spacing will get exponentially narrow in that system size. So any cyclicity is going to go to exponentially long times.
So because you're kind of looking at the limit, and somehow the time compared to the...
Well, so this statement, actually, I think you don't really need to take a limit. You can just say, do my eigenstates have this property that they agree, with appropriate errors, but that they agree with what I would estimate from a Gibbs ensemble? Because this doesn't say anything about actually the time dynamics. If this holds true, then any observables you measure in a local box will agree with the equilibrium properties, even if I set up an initial condition. I was thinking about putting this calculation in. Even if I set up an initial state which is not an energy eigenstate of the many-body system, it's some superposition of energy eigenstates, and you might think that there's phases and all kinds of things as the time evolves. If this condition holds true, it doesn't matter. All local observables will actually just agree with the equilibrium at long times, because of, well, basically the dephasing will just get pulled out of the expectation values. Okay. So actually, Eigenstate thermalization as a hypothesis I think is an interesting one because it seems to hold in a lot of settings, and it is really the starting point for claiming that quantum stat mech is applicable to time averaged observables or observables that we measure in a big system, which would be isolated. So a key feature of...
Excuse me.
Yeah.
Do you know an example where we know it holds? For sure? Or like numerics is fine too, but where?
Yeah, so there's numerics on, I think, so you have to get away from integrable models.
Yeah.
So I think this, okay, I didn't double check. I think some of these papers I put at the bottom, these recent ones, Regal et al., Hughes, they studied some 1D chains that aren't integrable. So probably Ising models with longer range interaction, like Next Neighbor or something like that.
These are numericals.
Yeah, those are numerical.
30-side hardcore boson model. That's not integrable. What they look at.
Sorry, what was that?
It's a 30-side non-integrable hardcore boson model they look at numerically.
Okay, yeah. Yeah, and it's probably 1D.
Yeah, sure.
Yeah, but yes, that's right.
This might be a bit pedantic, but what do the boundary conditions around A look like? Or are there any restrictions on them when you define rho A, the equilibrium state on A?
So, okay, I have dropped all kinds of limits and sort of arguments about how you go to thermodynamic limits in time. But it doesn't really matter if you define this rho A equilibrium as being the trace of the Gibbs ensemble for the full system. so you take e to the minus beta h, then trace out A, then that's what I mean by rho A. So what the boundary conditions are. I mean, that's whatever it is, whatever A I take, that's what I would define it as. I'm not saying try to define a notion of Hamiltonian for A. I'm saying take the Hamiltonian for the full system, do the Gibbs ensemble, then trace. That shouldn't matter up to boundary effects, but yeah. Yeah.
One might have thought there'd be constraints on the side, how local you have to be, depending on the energy, excitation energy you start with, and the time for which you allow the system to evolve. How do you comment on those?
Local I need to be. So basically, I'm imagining that these energies that I'm thinking about are at extensive energies. So the system is, this is where I would think the system has a temperature. Okay? I'm away from order 1 energies. So local observable is, they should just agree with the thermal state, basically, is the claim.
So the thermal state, you
At
imagine
that
it's clustered in
temperature.
some way, so there's no, it has a scale where you expect the entanglement to persist in any case.
Sorry, I'm not sure I understood that
I
question.
mean, at the very least, there's a thermal correlation then.
Yeah,
And
that would be in this. I mean, this is really what you would calculate. Like, you know, doing quantum stat mech, this is what you calculate. And this is just saying, if you started the system in an initial condition which had an energy density consistent with that temperature, so it's thinking microcanonically, and it was really in that initial eigenstate, but then you calculated observables, they would agree with what you would calculate in the quantum stat mech approach.
it's just looking at constraints on this.
Okay, yeah, okay. So right. So in order for this to, the main physical argument here is that is somehow that, you know, everything will eventually spread through the system. Energy, entanglement, whatever, if I started in some non-trivial initial condition. I clump things up on one side. In order for this to be true, I need to have that the energy I clump up over on this part of the system eventually does make it to the other side of the system. And that's why you can see that it requires exchange in order for this to be a possible scenario eigenstate thermalization. So what if it doesn't happen? That is, if there's no exchange. So quantum statistical mechanics breaks for localized systems is sort of one way to think about it. If I have a system where conserved quantities don't transport, then the isolated system dynamics will not agree. So observables I would see in the isolated system will not forget what their initial conditions were, and they need not agree with the thermal state observables at that energy density. Okay? So Herr Boltzmann tells us calculate using this, and Professor Anderson says nope. Okay, so this is I put Anderson here because it's Anderson who first proposed the idea of Anderson localization, and he was talking about localization of well, what's mostly been understood since then is localization of waves. I'll talk about it a bit more, so that would be energy wave, particle waves, energy waves, non-interacting waves. But he also was thinking about this interacting setting of localization of energy and so on in a full model. And if it happens, then sort of all of StatMech breaks for these isolated systems. So let me just, as a little more motivation, without a lot of justification, but more to whet people's appetite, point out a few of the exotic consequences of believing that a system is some Hamiltonian system could be many-body localized. Well, these have sort of been discussed in the last few years in various works. So if you have a localized Hamiltonian system, the high energy density states, which we normally would describe as being thermal, may actually have quantum, topological, symmetry-breaking orders, which are not allowed in thermal equilibrium. So, for instance, the example here is of a 1D Ising model. If I have a 1D Ising model, say a transverse field Ising model, I know it can order, it can develop long-range ferromagnetic order at t equals 0. But if I raise the temperature at all, then there will be proliferation of domain walls in the system. It's an entropic effect. And so the correlation function, the magnetization, whichever, as Matt, does it matter? Ashwin told us about how to measure long-range order in the last day or two. All of the correlation functions will decay exponentially because of the proliferation of defects in one dimension at finite temperature. But if I have a transverse field Ising model with sufficient disorder in it, then the claim is that you can go to a finite energy density eigenstate, and you can actually find, well, all that means is that you put in some finite density of domain walls in the system. That's how you got to that energy density. But the system is localized, and they can't move. And so if I measure connected correlators in that system, I would find that they have sort of a random value depending on what initial state I put the system in, you know, because this is frozen, so this correlation would be minus, and this correlation would be plus. So depending on exactly where I look, there's a frozen correlation, but it doesn't decay on average at long distances. So there's long-range connected correlators. And similar arguments have been made for freezing of topological, sort of developing, you can call this something like glass order because the magnetization pattern is frozen and it depends on what state you start. So it's a frozen order depending on your initial conditions. Similar arguments can be made for generalizing topological order in a disordered toric code, or this is a picture from the Levengo topological paramagnet, that indeed if you put disorder into these systems and they many-body localize, which is an assumption that you can make plausible arguments for, then you can go to finite energy density states and still have a well-defined notion of topological order, suitable modifications to the ground state. Okay.
Can I ask you a question? When you go one side back, I mean,
Yeah.
so what property of topological order you keep? I mean, we're of course interested in quantum information as well. Would that be useful as a quantum memory at finite temperature with this order? I mean, it's different from having, you know, one state with topological order.
Right. So that's a good question. So there's no finite temperature anymore. So it's that I can set up the system in some. Basically, the point would be that in these, I could put in states under its own dynamics if I have the toric code and I perturb it. So I have a closed system. I perturb it a little bit so that now my charges would normally disperse, right? So they start moving, the defects start moving. Then if they can move through the system, diffuse through the system under its own dynamics, they will screw up whatever I've encoded in the topological subspace. But if they're frozen, they don't. Okay, so now how you actually use that is delicate. But it's an idea which I think actually has come up a few times in the last few years, is that disorder can somehow stop defects from moving effectively and therefore stabilize the topological protection.
Yeah, people have analyzed the model with toric code.
That's right.
It's this order, of course.
That's right. So, but here the idea, I mean,
It's slightly different.
it's a little bit different if I imagine that I have a classical bath still or something that thermalizes the system. Even with disorder, the disorder might slow down the diffusion of the defects. But because it gets hit externally all the time, they keep moving. And so finite temperature, again, even in the disordered setting, would decohere the system eventually, right? Decohere whatever you've tried to protect. But if you're just thinking about the closed quantum dynamics, the disorder can prevent them from screwing themselves up, right? And also because we're here, so localized eigenstate. So if I have a many-body localized eigenstate at high energy density, it has been argued that these would have entanglement entropy obeying an area law, not just mutual information obeying an area law. And so it's a much stronger statement. If I look at these many-body eigenstates, then the entanglement entropy between a subsystem and the full system will scale as the perimeter, the boundary of the subsystem. And that should be contrasted with ergodic eigenstates. So if I had a system that satisfied eigenstate thermalization, then if I tried to do this calculation of entanglement entropy of the mix, of exactly this quantity, then the reduced density matrix would agree with the thermal reduced density matrix, And therefore, the entanglement, the entropy that I would calculate would agree with the equilibrium entropy, and I would get a volume law. Okay? So this is essentially saying that you can go to high energy density states in these strongly disordered systems and still get a lot of features of those many-body eigenstates that look like ground state properties. And it should be surprising in some sense, because when I go to high energy density, just remember, in a typical system, the spacing between eigenstates is becoming exponentially narrow. Right? There's no gap. There's not even a quasi-gap. There's lots of states. Yeah.
How relevant do you think that is physically? Because the state that has if you're at some level and there's another state with an exponentially close energy, to get there, you would have to do some extremely non-local thing. So do these things feel the nearby states, do you think? I know that's kind of a vague question, but should we, like...
The notion of feeling is not so vague, actually.
Okay. Right, so like perturbation theory, you will not see those until a very high order.
That's correct, and that's actually where most of the arguments that this exists, perturbative arguments that many-body localization exists, come from.
Okay.
But there is some notion of states feeling each other, which is that the level statistics of many-body localized eigenstates are Poisson,
okay.
Or conjectured to be, and it works in numerics. And in an ergodic phase, they exhibit level repulsion.
Okay.
So your random matrix theory ideas go through, but even though you've got this exponential density of states for the Hamiltonian.
So these things that have Poisson distributed, these are the eigenvalues of the reduced density matrix?
No, these are the eigenvalues of the full many-body Hamiltonian.
Okay. Oh, I see.
As opposed to, and that's different than, we'll see in a minute.
I understand.
Yeah. Okay, so any examples of, either of these? So nobody's proved much except for numerically about ETH, and there's very little known really rigorously about many-body localized Hamiltonians either. So, okay, so I put commuting Hamiltonians here because this is quantum information-oriented conference. Commuting Hamiltonians have integer spectra and nothing moves. So they're sort of localized in a trivial sense in that there's no dispersion of anything in those systems. But that's not really what we want. What we want is a generic Hamiltonian where, in principle, things could move. Energy, particles, whatever could move. So maybe a way to frame that, although I haven't thought about it until this minute, is if I could take a model and make an arbitrary small perturbation to it, then I would still have this property of localization, would be the key thing, as opposed to that being a singular effect, which it would be in clean commuting models, like clean Tor code. You'd expect it to be a singular effect. So the examples for many-body localization are strongly disordered models. So we have single particle Anderson localization, I'll tell you about in a second. Then adding perturbative interactions to single particle Anderson localized starting points, which is what reinvigorated a lot of the study of interacting localization, some arguments there a few years ago. And then a bunch of numerical studies of strongly disordered models, mostly in 1D. So let me give you some flavor of that. So what's the simplest example of localization? Well, it's actually to have non-interacting particles which are strongly disordered, and we actually just go back to Anderson localization. So here I have a Hamiltonian for a system of, it actually doesn't matter very much, but let's say fermions, which can hop, that's the first term, and they have some disordered on-site potential. Okay? And that potential is chosen from some distribution of width W. And what happens in the sort of simplest picture of Anderson localization is that turning on this hopping between the sites perturbatively is trying to delocalize the single particle wave functions between sites. But this off-resonant hopping, it's very weak hopping between very different levels, fails to hybridize the sites at long distances. So basically, I have n single particle levels, and they, roughly speaking, have both a location in space and an energy. They're not extended through the system. And the sort of caricature is that here's the energies, here's the n levels. This spectrum is Poisson. The level statistics are. And the typical states will decay exponentially from some central place where they're well defined with some localization length. You see, that's sort of the simple picture of strongly disordered single particles. Going back to Phil in 1958. So this is sort of a trivial example of many-body localization in the sense that the full many-body eigenstates of this Hamiltonian are just Slater determinant states. I build them up by filling these fermions. And those states really are just put a particle here, put a particle there, put a particle there, put a particle there. Their energies, again, will be Poisson distributed as many-body energies. And if I make cuts in them, entanglement, entropy cuts, etc., I'll see area laws. All the properties I just told you about hold. But this is because secretly these are free systems, or not so secretly. Okay? So the much harder step is to now argue that if I start with this set of states and add in interactions very weakly, that that indeed the many-body states, which are exponentially dense, fail to significantly hybridize and delocalize the system. Okay. So now you think of it as a perturbation problem where the states you're moving between are the 2 to the n occupation states, sort of corners of Fock space, and the interaction is hopping you in the Slater determinant space. And so there's 2 to the n states, and they're very dense. So there's no way that your small v perturbation is ever actually smaller than the spacing between the levels. But as you said, maybe it doesn't matter, and it's okay. And that's the argument that Bosco, Lehner, and Altschuler in 2006 put together in sort of a really big perturbative work to argue that indeed there's a finite range of perturbation V in which the expansion for particular eigenstates starting from there converges, and that argues that those states remain localized. All their properties remain like the single partically localized limit.
So this is some analytic work you're saying, it's perturbative.
It's, yes. It's analytic perturbative work,
'Cause you could also
but it throws out it throws out lots of things. It's very complicated perturbation theory. And I don't think you would say it was rigorous, but it is analytic and detailed. So maybe a way to, I don't even think you would say it was exact, actually. So sometimes you say things are exact but not rigorous. I don't think you would even say
But these
that.
things are gapped, right? You start with a gapped system, no? Because these particles are localized.
But I'm not starting with the ground state.
Okay, yeah, but...
So I'm starting,
Okay, no,
so here's, say that there's a most, I don't know, say that there's a gap. So here's my gap. Here's my ground state, here's my gap. I'm working way up here, where the typical level spacing is e to the minus n times whatever the entropy is up here. There's really no gap, if you just think about the many-body levels. So, but it was this argument due to Bosco, Lehner, and Altschuler which actually got a bunch of people interested in, I think, originally trying to show they were wrong, that this couldn't happen, that high energy density eigenstates could not remain localized when you turned on interactions. And eventually sort of deciding by studying a bunch of exact diagonalization in small 1D models mostly, that actually it could happen. And you could have...
Sorry, if you're saying, you just have many particles, right? I don't know what you mean by the ground state there. That's not the vacuum there, right?
Oh, the
Or
Hamiltonian...
you're sitting in a thermal state, no.
No.
You just have to fill it up to some Fermi level, that's where it's working.
Okay, so yeah, so say that I have, I don't know, those are my single particle levels?
Yeah, and you just add, yeah.
And then I fill some of them, maybe I
Yes.
put
And
some
then
number,
Yes,
right? That corresponds to one of 2 n states over
Yes.
here, right?
sure, yeah.
Okay, so,
And then the gap is to determine, get one mole out and then add one extra mole of the,
No
oh,
sharp division.
Oh, okay.
there's,
why you're not fixing the particle number?
I can fix the particle number, I will still have exponentially many states. if I say how many states in this picture, which is basically, you could actually, maybe this is useful. So say that I look at it as these, I shouldn't change notation, these energies, n alpha, right? And these are some random quantities. So now I ask the question, of which there are n, right? These are all order 1 random quantities. So now I ask the question, how many states, so there's some ground state, how many states are there which are consistent in some little energy window which is extensive, of order n, or whose middle is of order n, and whose middle energy. And that's going to be lots of different things, lots and lots of different states, which correspond to different fillings. Yeah. Okay, so I would say these are, in numerics it's becoming increasingly clear that many body localized systems may exist. These perturbative arguments are there in short range models. What we actually were motivated by was to come up with some more detailed theory that you could do something with in a model a little more analytically, which is to come up with a mean field model for the localization transition. So say you could tune some parameter, some v, and at some point you should have a transition from localized to delocalized. And we wanted to have some more control of that. So we did something, we decided to look at something which actually, I think I got to know the model because of a quantum complexity type conference a few years ago at ICTP, where it came up in the context of adiabatic quantum computing. So, I'll show you in a second why. So this is sort of the technical goal, which is that we wanted to find a mean field model for the many-body localization transition and to be able to study the wave functions in that model and so on, to be able to see whether there are, this is sort of a technical point, finite energy density mobility edges. So you could imagine that in this Hamiltonian, as I change my energy, at low energies maybe it's localized, and then above some energy density the states become delocalized, and eigenstate thermalization holds. It's very hard to show that in any particular model, though it's believed to happen. And then localization is sort of, so here's some motivation again from optimization. It's kind of the ultimate glass. Everything is frozen, right? Everything is localized. And so is there any connection? I don't know, that's a little bit vague. So the model that we decided to look at, and which turned out to be kind of useful, is the quantum random energy model, which some of you who've attended talks arguing about whether adiabatic quantum computing works might recognize. But let me present it this way. This is a model that actually comes from spin glass theory. And it's the simplest spin glass, is what it's often referred to, because it's built out of what's called the classical random energy model, where I take 2 to the n states, and I just give each of them a completely random energy. So it's an unstructured energy function, if you want. And for those of you who know spin glass theory, this is sort of an interacting body generalization of the Sherrington-Kirkpatrick model. But it's a completely non-local model. So this question of localization in it is a little bit fishy. But that's something we gave up a little bit because we were looking for mean field sort of analytic tractability. We're hoping to capture some physics that might show up in real localization transitions. And what I do is I take this classical random energy function on n diagonal bits or spins, and I just apply transverse field to it, and this is what provides the quantum dynamics. Okay? And it's useful, so you can think of this as being n qubits in a transverse field with some energy function. It's also useful to visualize the hypercube, where the corners of the hypercube are just the z configurations. And this transverse field is really just a hopping term on this hypercube. So this model is very much like Anderson localization on the n-dimensional hypercube, single particle Anderson localization on the n-dimensional hypercube. But it has an interpretation in terms of n spins. Okay, so now I want to, how much time do I have?
About 10 minutes.
Oh, okay. So let me take you very quickly through some of the features of the model. So the classical limit, when you turn off the transverse field, it's called the simplest spin glass because it exhibits, maybe let's ignore height, it's very easy to solve, but let's ignore it for a second. It exhibits two phases if you just calculate e to the minus beta h and ask what does the free energy do. So this is statistical mechanics. There's a high temperature phase, which is a paramagnet, and then there's some critical temperature below which it freezes. That is, the measure condenses, just the statistical measure on the states condenses onto basically a single state, roughly. And that's why it's sort of a simple model for this random, this is viewed as sort of the random replica symmetry breaking glass transition, random first order transition. The quantum random energy model, actually the statistical mechanics, so this is solving for what the phases of this measure look like as you vary temperature and transverse field, actually was solved. This model turns out to have an exact but not rigorous solution by what's known as the replica trick in an imaginary time representation with certain ansatzes for order parameters. Let me skip over that. So what you get is actually a phase diagram which isn't so hard to understand. So the point is that this is the ground state down here. This is low temperature, that's high temperature. Large transverse field, small transverse field. At high transverse field, you expect that the transverse field dominates and the spins all just point along the transverse field. That's your quantum paramagnetic phase. At low transverse field, you get that classical phase diagram that I showed you a second ago, where at the low temperatures, it's frozen, and at high temperatures, there's a classical paramagnet. And these blue lines are first order transitions in that thermodynamic phase diagram. What is actually missing in this phase diagram is any notion of what the actual dynamics induced by H are. This is just evaluating the properties of this measure. Okay? And so if you take the sort of closed quantum system point of view a little more rigorously, what you find is that there is a localization transition. So on this side of this curve, so the blue region, the system is ergodic. And so even if you had the closed Hamiltonian with no external temperature source, you would say that statistical mechanics is a reasonable thing to look at for long-time observables. And these phases, this quantum paramagnet and this classical paramagnet and this first order transition between them actually exist as thermal phases in the closed dynamics. On the other side of this curve, the system is localized, and which actually tells you that if you just take the Hamiltonian of the system seriously, this isn't meaningful, right? That transition is inside of a localized regime. I can't freeze there anyway, because I can't cool into it, I can't do anything. If I really try to reduce the energy of the system into this regime of the phase diagram, the system gets completely frozen. Or it's hard to say how you reduce the energy when you are imagining it as being a closed system. But if you started in a configuration which is consistent with that energy, then it would be completely frozen. Observables would not agree with thermal observables. And this transition goes right through what in the StatMech analysis of this measure is just a boring high temperature paramagnetic phase where all the observables, all the magnetizations are zero, basically. Due to thermal fluctuations. So, what do I mean by that? Let me jump ahead to local observables, because I think this might make clear a little bit what I'm saying. As I said, in ergodic phase, I expect the local observables to agree with those of the thermal ensemble, the thermal equilibrium ensemble. And so if I look, for instance, at the magnetization of a spin in an eigenstate, it should be basically the magnetization that I would calculate at that energy density for for a canonical average. Okay? That's what equilibration means. Which means that if I look at the derivative of that magnetization with respect to a finite difference derivative eigenstate to eigenstate, this magnetization derivative should be very small. It should be exponentially small because the energy spacing is exponentially small. Right? Whereas in the many-body localized phase, this difference would be order 1 because these states really have nothing to do with each other. And in this quantum random energy model, there's a subtlety, which is that, like I said, it's a little bit pathological because this energy function is very non-local. But if you look at commutators, you can see that basically the sigma z magnetizations, sigma z operators behave, at least they only change energies by order 1, and so you can interpret them as being the appropriate local observables. And what you see, if you look at exactly the quantity I just told you, which is the derivative, the discrete derivative across the entire spectrum.
So you are just looking at the eigenstates and that observable, and
Yeah.
then you get that dynamical phase diagram that you know, did.
Well, that's not how I calculated it. I just wanted to give you a picture of it. Yeah, but yes.
Yeah, but I mean, that's the criterion where you
That-
call
you-
something
you can take that- yes,
localized
you can
or
take that as-
ergodic, right?
that's right.
That's the
Yeah.
basic
So numerically, I can take any number of criteria, and they all agree, and this is one of them.
Right.
Analytically, we try to estimate
yeah.
where.
Oh, you have an
waveforms-
analytic analysis.
We have
to
a
that.
partial analytic analysis, yeah, which I'll hopefully be able to flash through a little bit. But I just wanted to give intuition about what it means. So this is the largest system size. These are what I call spider diagrams. They're basically just histograms. So if you take a vertical cut like this, that's a histogram of the value of the derivative of the magnetization, the delta derivative of magnetization from one many-body eigenstate to the next, histogrammed in little energy windows, which is the energy center of those windows is down here. So at low energy densities, you see that it's strongly peaked around 3 values, which is basically that the magnetization can be plus or minus 1, so the 3 values are plus 2, 0, and minus 2. Whereas in intermediate regimes at high energy, or infinite temperature, or high temperature, if you were going to define temperature, you actually get that this is basically 0, that all these derivatives get tight. You can actually, the fact that this has width and these look narrower, that's controlled by the finite size, and you can estimate that this one should look like this and that one looks like that. But let me not go into it too much. So basically the idea is that at these high, so the ground state is over here, this is the lowest energy. At high energy densities, I have a system whose eigenstates look thermal, or whose magnetizations agree with the thermal magnetization of 0. And at low energy densities, roughly below this point, I have a whole range of phase where the classical thermal analysis would tell you this magnetization should be 0 because I'm in that paramagnetic regime. But this tells you that in each eigenstate it's actually just frozen.
The right-hand side is just finite length.
The right-hand side, what, over here?
Yeah.
This would be, this is essentially negative temperature. This is very high energy density. Yeah. Okay, so the, what shall I talk about? So let me tell you where some of the analytics can go. So the simplest, or not simplest, okay, so how do we try to calculate something about this? So we just look perturbatively starting at the gamma equals 0 limit. And we start with a many-body wave function, which is just some corner of this hypercube, right? And then the leading perturbative wave function is going to be if I now perturb with gamma, and I ask what's the amplitude of the wave function at some other vertex of the hypercube, the leading perturbative wave function is going to be the sum over paths that go from my starting point to that point on the hypercube of gamma divided by an energy denominator, the intermediate state. And I have written forward scattering here because the approximation we make, which seems to work pretty well, is just to ignore longer loops. So whatever the first order in perturbation theory is, so the shortest path, you just don't worry about anything after that point. So that defines my wave functions that I'm going to actually be able to analyze. this we can take as a criterion for localization that the amplitudes that I estimate in this approach decay out to the system size. If they start growing, the perturbation theory is clearly broken. It indicates, physically what that indicates is that there's resonances happening. And so if they grow at some distance which is inside the system, then I expect that the resonances will proliferate through the system, and that corresponds to my delocalization. So this has sort of physical, this expression has a nice interpretation of thinking of directed random polymers on the hypercube. So I basically fix the end of a polymer where I want to start, I fix where I want it to go, and then I have some statistical average of all the possible routes it can take with weights. And there's a couple of different things you can do having made that identification, but let me just take you through a couple simple heuristics that get you a lot of the way there. So if I imagine starting in a state whose energy is extensively away from infinite temperature, which is at zero energy, right? Then the gap in this, then the states, the vertices of the hypercube that I move through in these paths are essentially independently sampled random energies from my original energy function. And those independently sampled random energies are going to be essentially sampled from the infinite temperature regime of the classical model, which means that they essentially are zero with root n fluctuations. Okay. And this energy I started with is order n, which means that this gap in the denominator is typically of order n, which is very big. So it has a long tail, but you can control it. Let's ignore it for now. So let's just sort of naively go ahead and expand this expression. Notice that, assuming that this is much bigger than that, and then take an average. Okay, really what I'm doing is taking the typical value for this expression, and what you find is that the typical amplitude at a distance n grows as n factorial, that's the number of paths on the hypercube, times this gamma over initial energy to the n. And so if we demand, notice that as n gets very big, this will always grow, the n factorial will always eventually win. But if we demand that it decays until at least the system size, you actually predict, you get a gamma critical, which is the energy density of this initial state. Okay? And that's exactly what that agrees basically with the numerics, up to finite size corrections, I'll show you in a second. And it's what I plotted on the curve, on that dynamical phase diagram, is that gamma critical one. So this argument needs quite a bit more care if you start with a state which is already at infinite temperature, so a state of energy zero, or roughly zero, because this denominator is now not small, or not big, sorry. So for those central energies, you can do a few rigorous things, and you can do some not so rigorous thing that I'll do on the next slide. But you can get a feeling for it, which is just, we can bound this amplitude to go to some distance n by just, or not quite bound, but we can estimate it by just estimating what's the greediest path on this hypercube that goes to distance n. And essentially, you have capital N choices for the first step, you have n minus 1 choices for the next step, etc. And eventually you will find some scaling for the greedy path, which goes like this, the amplitude for this sort of greediest path in this to distance n. And that, again, if we make the same demand that this path doesn't cause the amplitude to become large, gives an upper bound on delocalization threshold, which goes as 1 over root n, the system size, when you're working near infinite temperature. Counting these resonances more carefully gives a log correction. It's even a rigorous log correction. But you can also actually, I'm hesitant to even discuss this because it's going to make the mathematically rigorous people here want to run out of the room and beat me up or something. But you can also actually solve this problem using this classic replica trick. So I have random polymers. I want to know what their typical, the distribution of the typical amplitude is at a given distance. And that means I want to know what the expectation value of the log of the amplitude is. And roughly speaking, I can calculate that by taking this replica limit. I imagine replicating the system n times, disorder averaging that n copies of the system, which means taking a moment, subtracting 1, dividing by n, and then taking n to 0, which means that I didn't replicate the system at all. But it works. So if you do this and take it at face value, what you have to evaluate this moment is the statistical model of n polymers that are interacting. And you can actually take a one-step replica symmetry breaking ansatz for it. You get some free energies. I will explain it to anybody who's interested. There's a recipe you follow. It's sort of completely concrete. And what's beautiful about it is at the end, you get that gamma critical is this. Okay? It just calculates it. This is the answer. All right? In leading 1 over log L corrections, and you can get higher order log corrections and so on, just from doing the algebra. Okay? And how does it work? Well, so this is some mixture. This is the numerical phase diagram. My energy is on the left axis. Gamma is here. This gamma equals E critical transition is the heavy blue line that I've drawn here. So this region here is supposed to be delocalized. The regions over here are the localized regions. These contours you see here are from 4 different system sizes. These are contours of level statistics, actually, but I didn't explain that, so it's okay. And those 4 x's are what that formula gives you. There's no fit. So basically, the idea is that this boundary, which you see in these 4 colors, as system size gets bigger, this is finite size numerics, should sharpen into this triangle. That's what we believe. And they actually are pretty good out here, but near infinite temperature, the sharpening is going as 1 over root n log n. And you can just plug in this explicit formula with root pi's and stuff like that, and just say, okay, at n equals 8, that's what that formula says. Okay? And it basically agrees with what we see numerically. Which actually I found kind of magical when we did it. But okay, so I think I'm basically done. I spent more time talking in the beginning about eigenstate thermalization than I had planned. But I do want to say one thing about adiabatic quantum optimization. So, since it was in my title. The random energy model has been studied in the context of adiabatic quantum computing as an unstructured search problem. I have completely unstructured energies on the hypercube, and I want to find the ground state. I can imagine taking my transverse field and slowly turning it off, and it's an adiabatic computation of this ground state. And it's been studied in a couple of contexts, argued for various reasons to have an exponentially small gap. This is the dictionary. Annealing the transverse field is like searching for the ground state. So now the thing is, you know you're going to fail, because this is just unstructured search. So you can even come up with complexity theoretic lower bounds or information theoretic lower bounds that you have to fail if you go faster than exponentially slowly. But you can ask the question, what is the final energy density that you get to when you do go a little bit faster? You can think of that as an approximate search for the ground state. Okay. So then you can ask the question, well, what's the scaling of the final energy density with time? And that is related to how hard is it to approximate. Now, this is still unstructured search. So I can give you lower bounds, which I hope are correct, but I think they are. Basically, I would expect that I know it'll take exponential time to find the ground state. It should go as 2 to the n. Okay, that's here. So what I've plotted here is the log time divided by n. So this is a rate for my exponential of the time. And the curve is supposed to be the final energy that I would find, the final energy density that I would find as a function of that sweep rate. Okay. So I will get to the ground state if I go exponentially slowly. Okay. There are 3 conjectures for what this function would look like. And one can, now I believe it is an open challenge to actually calculate it in this unstructured problem. I think it'd be kind of neat to do. And I don't know. There's only one calculation of a curve that looks like this in the literature that I could find, and it's for a mean field ferromagnet, so it's kind of trivial. Simplest conjecture is that if you scale this rate function so that your time goes less than 2 to the n, but still exponentially slowly, you just hit a brick wall. You either get the ground state or you get an infinite temperature state, so zero energy density at the end, right? You can take a lower bound, which is essentially just an information theoretic bound from saying that the number of states with a given energy density down here as a fraction of the total number of states is given by some appropriate entropy, which you can calculate in this model, and then say, well, so now I have a lower bound if I think of it as an approximation problem that I will find one of those marked states. And that gives you either this curve, or if you allow yourself a Grover speed up, a quantum speed up, this curve. Okay, I don't know the answer. I tried to run some numerics just for like yesterday or something, but the sizes are way too small to get anywhere near this regime, so whatever. Anyway, there's a connection to adiabatic quantum optimization to throw out to, you know, the aficionados. Anyway, okay, so here's my summary. The quantum random energy model provides a mean field model of the transition at finite energy density, that's up here. We think we can discuss exactly what it means. It's a first order dynamical transition that is not reflected in the thermodynamic measure at all. You can do a perturbative treatment in this forward approximation and do some more rigorous things than what I showed you. Also, this replica thing seems to give you the right answer, so it gives you some ability to calculate stuff about this transition in this model. It's inside what's normally called the paramagnetic, classical paramagnetic phase of this model as a spin glass, which is roughly saying the StatMech people, spin glass people who treat this as a beautiful model for the random spin glass transition, as usual, have not quite connected the thermodynamics to the dynamics, and it matters. And then there's this sort of funny feature of this slow approach to the thermodynamic limit near infinite temperature. Right, so I think I mentioned most of these questions as I went, so okay, thank you.